Welcome to the Machine Learning Internship by Internship Studio. In this internship module, we are going to discuss about the linear regression. We have a basic idea regarding the linear regression previously, and also we saw a hands-on example of how we are going to calculate the intercept values for the linear regression, and how we are going to calculate the RSS values, and how we are going to plot it respectively. So we also saw the code part of that, right? But now either ways, like, we'll try to understand more into the linear regression. Why? Because regression is a sort of like core algorithm for the machine learning. So it's important that you have a very good idea regarding the regression. So that's the reason I'm doing an extended discussion regarding the linear regression part. And there are different variants of the linear regression as well. So we'll try to understand regarding the algorithm in a more deeper sense, and also regarding the different metrics that is available or that are available for assessing the regression part, and what are the different metrics that are available for evaluating the model performance. Yeah, as we were discussing previously, linear regression is a very simple approach to supervised learning, and you have classification and regression both, right? We are dealing with the regression part here, and it assumes that the dependency of the whatever the output y and the x variable is linear. That's the reason it's called the linear regression, right? So you can see the regression functions as well, and if you see, basically, you'll have a straight line that is plotted across, which is a blue color line that you can see here. And yeah, and linear regression is very simplistic, and it's also extremely useful, both conceptually and also practically as well. Now you have to understand what is the difference between correlation and regression. If you are plotting a scatter diagram, then what you will see is you'll try to understand the relationship between two variables. Once you understand the relation, in the sense, like, which is the correlation that we are speaking with, in the sense, like, when we have this scatter plot, right, we'll try to understand, is there any positive correlation or negative correlation, or there is no correlation at all, and we'll also try to interpret it with respect to the Pearson correlation coefficient, right? So we want to check the correlation coefficient also, which is the measure of the relationship between two different variables. If you see, basically, in regression, what we have, suppose if it's a two variable regression problem that we were discussing, which is a very simple one, there you can see that you have this two different set of variables, and you are plotting the scatter plot, and based on that you are trying to check, right, like, if x is increasing, is y is increasing or decreasing, what is the type of correlation that you are seeing. That is what the strength of the relationship that we are trying to see, and according to that we are trying to plot or fit a linear model, which is basically our linear regression that we are trying to fit upon. Yeah, and also, like, there is something called this causal effect. There's a saying that correlation is not equal to causation, but we'll not try to go more in depth into that. We'll just try to understand correlation as of now, what exactly correlation is, and with respect to the correlation itself, we are trying to do the regression analysis. And then if you see the regression analysis here, you have two different variables which are important that we have to understand or keep a note of. They are dependent variable and independent variable. Dependent variable is nothing but the variable which you want to predict. So you have your target variable, right? The target variable or dependent variable, these are the same thing. You have different names for that. And then independent variables are nothing but your features. So you have this different set of features with you, and with respect to the correlation between the feature and the target variable or the dependent variable, you are going to make a respective prediction. That's what we are trying to do in the regression analysis part. And in regression analysis, we are trying to predict the value of a dependent variable based on the value of at least one independent variable. So how much correlation we have, or how much a particular variable is contributing to the prediction of the dependent variable. And also, if you see, basically the ideal case is that all the variables should be independent to each other. They should be dependent on the target variable. They should have a dependency with the target variable, in the sense correlation and collinearity with respect to the target variable. and there should not be like among themselves there should not be any dependence that is there. That's the reason they are referred to the independent variables. But the problem is, even then, there are some relationships that exist between themselves. So you cannot tell that all the features that you are taking are completely independent of each other, and some cases there's some dependency that is always existing between them. So that is where the concept of interactions come into picture, and we will look into that. At the end, we'll try to understand more into that. If there is a dependence between the variables, how we are going to deal with, or how we are going to take them also into the account. So as of now, just see that you have these two different variables: dependent variable and independent variable. Independent variables are your features. And if you take a simple linear regression model, you have only one independent variable x, and the relationship between x and y is described by our parametric function that we are going to construct, which is a linear line in a two-dimensional, if you sense, and if you go to higher dimensions, it will become a plane. So yeah, so we are trying to plot a trying to plot or fit a linear model or linear regression model to the data that is in hand with you. And the changes in y are assumed to be caused by changes in x. That is where the correlation comes into picture, right? Suppose x and y are not correlated at all, there is no correlation between among themselves, then there is no point in constructing the regression model as well, right? Why? Because there is no parametric relationship that is existing between both of them. So there should be some dependency that is there, and we are trying to formulate that dependency using the mathematical model that we are going to construct, which is the regression model that we are referring here. And what are the different types of relationships that are existing? So if you see, you have a linear relationship here. In the left side, you can see this kind of relationship, right? So a linear positive relationship that is present between x and y variables. And you can see yeah, you can see this kind of relation where with respect to the x values, as the x value increases, y value is decreasing. So it's also one linear relationship. So the y value is decreasing linearly. So these are the general relationships between the variables that you see across between the dependent variable and the independent variable. In the sense here, x is our independent variable, right? And y is the dependent variable. And using x, you have to make a prediction of the y value. Suppose x is the house price, and sorry, x is the square feet, like flat square feet, and y is the house price. So with respect to the square feet, you are trying to predict the value of y. If somebody tells that you have some thousands square feet apartment, so you are going to predict the house price. This has this much square feet, so it can be like the price of the house can be this much. So we are making a prediction with respect of the y value with respect to the x value. Once the model is trained, or once you have constructed the model. And proceeding further, you have this curvilinear relationships as well. So you can see the relationship among the x and y are not linear, right? They have a bit of curve here. So these kind of relationships may also exist. So it is not the case that every time you are only having linear relationships, you have some other sort of relationships as well. So if you see, this is also some sort of linear relationship, but you have some curvature there. So that's the reason it's called a curvilinear relationship. And then what are the different types of relationships that are existing? In a sense, you have the strong relationships here. So we have this relationship in the sense how the scatters, or how the samples that are spread across. If you see, you have a tight spread that is occurring between, right? So if you see this kind of relationship, you have more scatter here. So they are scattered across, and they are not tighter, or they are not even fitting the linear model is also not a easy deal here, right? So you can see the type of relationship that is existing. So it is scattered across whatever the samples are there, which is a bit difficult for us. And even the error that we are speaking also, maybe compared to these kind of relationships, it will be more here. So hope you understand the difference between these two different relationships, and it is preferred that if you have this kind of strong relationship existing between the variables, which will help you in constructing appropriate proper model. And then what are the types of relationships that are existing? And if you see, there is no much relationship that is existing between here, right? And again, like here the scatter is more, and here the scatter, they are not, data samples are not much scattered across, but you can understand, right, regarding the relationships part. So you can see that there is no relationship that is existing between x and y. So no linear relationship that you can fit a model, or you can try to formulate in a linear regression sense. So you can see both of the cases there is no relationship that is present. And coming to the main simple linear regression model, you can see the y value here. Y is your dependent variable, and beta naught is the y intercept. So beta naught will be your intercept. If you speak of, or if you take it as a line case, well, if you take the equation of line is nothing but y equal to mx plus c, right? M is your slope, and x is your variable, and mx plus c is your intercept. In the same way, beta naught will be your y intercept, and beta 1 is the slope coefficient, as I was referring to whatever the m I was speaking in the line example, right? Similarly, beta 1 is the slope coefficient, and x1 or xi is the independent variable. So yi is the dependent variable, and xi is the independent variable, and using this xi value you are going to predict the yi value, which is your dependent variable case, and is a linear component. So this is linear, right? You can understand that, very much understandable. And you have something called this random error component that is present, so which is a irreducible error that will be always present, whatever may be the model that you are taking, and how much ever the training or exact fitting that you are doing, that epsilon error will be always present across. And then if you see, you have this simple linear regression model, and if once you have plotted that, you can see what is the observed value of y for xi. This is the observed value, and this is the predicted value. So once yeah, so once you have fitted the line, so with respect to these set of samples, you have fitted a line which fits every all the data points in a appropriate or approximate well manner. If you try to make a prediction of xi, you can see that actually the sample is this, but because of the model, as the model is linear, and we are also trying to understand or fit your data in such a way, fit your model in such a way that it is not overfitting as well, right? So considering all the set of considerations, you can see that there's a error that is there, right? So this is the error, so this is the sample, and this is the value that you are predicting. So this is the error term that you are referring to. So this is the predicted value of y for xi, and this becomes your random error of this xi value, which is your epsilon I. So yeah, so if you speak of the intercept term, intercept will be beta naught here. This is the intercept, and you can see the beta 1 as your slope here. So this is the slope of the line. So you can visually interpret the equation which we were discussing of in this way here. And then if you see, say simple linear regression equation provides an estimate of the population regression line. So this is the estimate of the regression that we are speaking of, and finally we are trying to do a estimation of the y value for the observation xi. For a particular xi, which is your observation, you are going to get your respective yi value. So that xi can be anything like x1 sample or x2 sample, anything with respect to that. Once you plug that into this equation, you are going to get your y1 or y2 respectively with respect to the x. So we are doing a sort of like a prediction with respect to the xi values. Yeah, the individual random error terms A have a mean of 0. So if you take a mean of that, it will be 0. And how we are going to obtain the coefficients of the beta naught and beta 1. So there are different types of methods that you can try out to obtain the values of beta naught and beta 1. So we have already saw in the previous model, right, how we can get the set of values, and there are different ways. So here the simple way that we can speak of is the least square method. So using the least square methods, what you are trying to do is you are minimizing the sum of the square differences between y and y cap. So yeah, y cap or y hat. Y hat is nothing but the whatever the predicted value is, and y is the ground truth. So y minus y cap will be your error term, right? And then if you do a square of it, it become your square difference or square error, and you are trying to do the minimization of this. So that is the reason it's the that minimizes the sum of square differences. So you have to find your beta naught and beta 1 in such a way that this is your minimum value. And once you substitute your yi hat is nothing but this, right? So whatever the output from the linear regression line, so it will be like beta naught plus beta 1 xi. So this is how we are going to take this. And interpretation of the slope and intercept. So if you see the beta naught, b naught is the estimated average value of y, and the value of x is 0. So yeah, if suppose like slope is 0, right, then it will be your beta naught itself, right, whatever the value that you are referring to. And beta 1 is the estimated change in the average value of y as a result of a 1 unit change in x. That is what the slope refers to, right? So you have the slope and intercept here, and you can interpret it in this way. And if you take an example of the advertising data, so suppose you have some advertising data, then what you are trying to do is you are trying to ask some set of questions by looking into this advertisement data. The questions are like, is there any relationship between advertising budget and sales? How strong is the relationship between advertising budget and sales? Which media contribute to sales? How accurately can we predict future sales? Is the relationship linear? Is there synergy among the advertising media? In the sense like now here the problem that we are discussing or dealing with is, suppose you have the example like you have this case of like the sales budget. So you have some sales budget, and your task is to spend this marketing budget. So you are from the marketing department, and you have the marketing budget with you, and your aim is to increase the sales. So obviously, right, for improving the sales, you will do your marketing. For that, you are giving different advertisements, and you have three different platforms that are there in which you can give the advertisements. So you have the TV, radio, and newspaper. You have these three different set of media platforms in which you can give the advertisements, and accordingly you are going to improve your sales. And if you speak it in a general sense, so one thing is you have to make sure that everything is contributing to the sales. That's the first thing. Why? Because suppose TV is there, so by giving TV advertisements, your sales are not improving at all, and whatever may be the advertisement budget that you are allocating, there is no improvement in sales. Then there is no relationship between the TV and sales, right? That is what the preliminary primary assumptions at least that we can make with respect to the relationship. If there is no relationship, there is no point in spending the money itself, right? Budget for the TV sales. So that is one question that previously we were referring to, right? And then if there is a one thing is like for all these three different set of like platforms or media, there is a relationship. There is a relationship for sure. And how strong is the relationship? Why? Because based on the strength only we are going to spend our budget also, right? In the sense like suppose for TV, there is lot of relationship, or there's a good amount of relationship, and you are getting by spending money or budget on the TV, you are getting very good sales improvement. So your sales are increasing a lot. Then it makes sense to channelize more of your budget to TV, right? So it depends on the relationship. If you see the newspaper, if you see the scatter plots that are plotted here, you can clearly see that newspaper advertisements are not that much affecting or improving your sales data. So there is no much improvement in the sales data that you can see. And TV advertisements have some significant amount of dependency, or there's a relationship that you can see, and you can see the improvement as well. As you are increasing the say TV budget, your sales are also increasing linearly. So so by seeing this itself, you can understand that there's a good amount of relationship between the TV media and the sales. So yeah, so this is what that is the reason we have to yeah, that is the reason you yeah, that is the reason generally like you are trying to do this EDA kind of visualizations, right? So that you can understand the relationship between the variables. And then if you see it here, Okay. Yeah. So you can see that you have this simple linear regression using a single predictor X. We are assuming a model here. This is a model that we are referring to. And then we have the intercept and slope as beta naught and beta one, right? And we have the coefficients or parameters respectively. And you can see the see the y hat that we are going to do the prediction, and how we are going to do the estimation of parameters by least square. So as we were discussing regarding the least squares, right, and also we have defined the error term as well. This is the yi minus yi hat, and which is your residual sum of squares. So if you try to do it for the individual one, so if you see there's a summation previously, right, so if you expand that and if you substitute the values of y hat here, you can see the same equation, right? So you can see the RSS value here, and if you are trying to, our aim is to finally minimize our RSS, which becomes generally our cost function or the error function or the loss function that we generally refer to in the machine learning or deep learning terms. So RSS will be our error function. We have to somehow minimize that, and how we are going to minimize that? You have only this beta naught and beta one values, right? Using which you will tune them accordingly in order to minimize your RSS value. Yeah, so for finding the set of values beta 1 and beta naught, you have the set of things. So you have this beta naught and beta 1, and you can calculate or you can get the respective values accordingly. So you can see the beta 1 and beta naught values that are obtained after performing the minimization or the minimum value that you can get. And you can see the advertising sales data. So now we are trying to feed the TV and the sales here. So how the sales and TV are related to each other, or this is a model, that linear model or line that we have fitted across a linear regression, using the linear regression to model the relationship between the TV and sales data. And you can see the points as well, and you can see the residuals as well. So this is the residual of the error term from the line to the point, if you consider. So we have all this set of different points, and you can see, right, we have these different residuals that are there. And standard error of an estimator reflects how it varies under repeated sampling we have. So this is the sample, or the standard error of the beta 1 hat, a squared sample error or standard error, and you can see the squared standard error of beta naught here that are calculated. So we are going to calculate in this way, and there is something called this confidence level as well. So a 95% confidence level is defined as a range of values such that with 95% probability the range will contain the true unknown value of the parameter. So once you take this beta 1 plus or minus 2 standard error of beta 1 hat, then you are going to see the confidence level or the 95% confidence level between the set of values. So yeah, this is the range that we were referring to for the beta 1. So we were discussing regarding the beta 1 here. And coming to the hypothesis testing part, so as we have already discussed regarding the hypothesis testing, right, in the stats part when we are discussing that, so you have something called this null hypothesis and the alternative hypothesis, right? So here the hypothesis that you are formulating is the null hypothesis is there is no relationship between x and y, and alternative hypothesis is there is a relationship between x and y. That's how, like, we have modeled our confidence scores, or that is how we are going to formulate our hypothesis first, and with respect to that we are trying to make our analysis further. So we can see that mathematically this corresponds to testing beta 1 equal to 0 versus beta 1 not equal to 0. Since if beta 1 equal to 0, then the model reduces to y equal to beta naught plus s, and x is not associated with s. Obviously, right, if you have got this kind of relationship, there is no relationship between y and x. So that is what we are trying to prove here with respect to the hypothesis testing, and that is where we are trying to take the t statistic here. So as we were discussing previously also also regarding the t statistic and the t distribution, right? Using statistical software, it is easy to compute the probability of observing any value equal to t or larger. We call this probability the p value. So with respect to the p value, we are trying to interpret, right? Generally, like we have discussed that the basic p value is 0.05, but here we have taken the threshold of 0.001, 0001 as your p value, and the t statistic is also calculated here with respect to the coefficient and the standard errors. So we are finally assessing the overall accuracy of the model. We are computing the residual standard error here, which is the RSE, and now we are trying to find something called R square. R square is nothing but is the fraction of variance. So there's something called this total sum of squares. So you have the residual sum of squares here, which is this, and you have the total sum of squares, which is this, and you can see how we are going to calculate the R square part. So 1 minus RSS by TSS, if you do, you are going to get your R square value, and using the R square value itself, we are trying to understand the fraction of variances and what is the performance of the linear regression model that we are referring to. So for regression also, we'll be having some set of metrics as we were discussing, or I have explained to you, right? So this is one such metric. So R square, using R square, you can do the goodness of it, or how exactly the model is fitting to the data. Yeah, and R square equal to R, where R is a correlation between X and Y. So you can, with respect to the R itself in the regression setting, you can try to understand the correlation between X and Y as well. So this is what we are trying to do, and we have calculated the residual standard error here, and we have the R square here, and we have the F statistic as well that have been calculated for the advertising data. And for measures, the different measures of variation that we were speaking of, so we have the total sum of space here, which measures the variation of the yi values around the mean y, and we have the regression sum of squares, which are the explained variation attribute to the relationship between x and y. So what is the relationship between x and y, that we are going to understand, and variation attributable to factors other than the relationship between x and y. So other than the relationship between x and y, what are the variations that are present? You are going to get the error sum of squares will interpret that, or it will give you those set of factors. So yeah, so you can see them pictorially to understand it in a more deeper sense. So you can see the SSR that have been calculated here, and you have the total SST, which is the, if you see it here, you can see the total sum of squares that is there, is a complete variation that we are referring to, and SSE is nothing but from here to here, from the model to the sample that you are speaking to, and this is the difference between that. So if you take a difference between the SST and SSE, you are going to get the SSR value. So this is how visually we are going to interpret and understand the different variations, or the different SST, SSE and SSRs that we are going to understand and interpret respectively.